Prafula will admit the participants as they come. So thanks for joining me today. Last time we talked about the path to AGI, and so we saw that one of the possibility to reach AGI would be to adopt Neuro-Symbolic AI. Neuro-Symbolic AI. So we're going to see what it is and how we can use it and examples of that. And in fact, we'll see that it's already there. Maybe we haven't realized it yet. Okay, so today Neuro-Symbolic AI. So I talk about some architecture. Mostly I've talked about some examples, challenges, and how to implement Neuro-Symbolic AI. Some application. I focus today mostly on mathematics and science, and talk about future direction. Okay. So here you see the illustration. Well, it's just like, it's a Gen AI, but you have a symbolic approach using symbols, relationship, and so on. On the left, it's more like the neural network as we know them today. So the hybrid approach will use neural networks, like LLM, large language models, would be like a neural networks, Gemini, ChatGPT, and so on. And with symbolic AI, that use like rule-based logic and reasoning, right? And to create more capable, interpretable, and adaptable systems. This is a cartoon from a survey, and I think in 2020 survey on AI, and they talk a bit about Neuro-Symbolic AI. So they had this funny cartoon. So before you had I think the mouse is Jerry, the cat is Tom, right? Tom and Jerry, right? So these actually, so this symbolic AI is the big cat on neural networks. It was a little mouse. So this was like in the 1990s on before, right? And then after 2010, thanks to deep learning, the neural networks, right, the little mouse, become like very strong. Now symbolic AI has been overtaken. Right? So this is kind of the cartoonish history of AI. In fact, it's more complicated again than that, but I think it's an interesting illustration. So there's the hypothesis of the neuro-symbolic approach is that neither like neural networks or symbolic AI alone can solve all the problems, right? So we combine the two, we can find something better, right? So that illustration here. So it's supposed to be a crossover between the cat and the mouse, between Tom and Jerry. So this is the neuro-symbolic AI. Okay. So quickly, I think that we should, you must have the intuition of that. Neural networks, the strength, they're very good at pattern recognition. They handle all kind of data, structured data pretty well. They learn from examples, so we need a huge amount of training data, all the data on the internet, for instance. Limitation is that it's a bit of a black box models, right? Some of the models have like billions of neurons in there, so it's difficult to know exactly what goes in there. The lack of interpretability. No, it's sometimes not that easy to know why the results is A or B or C. So it requires massive data, and we might run out data, at least text data. I might struggle with reasoning. But we have made a huge improvement, right, in reasoning, and we are going to see this later on. So it's not all true. Like now I gave some presentation on reasoning models in AI, and so LLMs can reason. You have these thinking mode or deep thinking models, and we talk about that. And thanks to the reasoning, there's a bit of interpretability. You can ask the AI, why do you come up with the results? And sometimes it will give you the answer. It might not be the accurate answer, but it will give you some answer. Symbolic AI is a bit more. So symbolic AI, just the definition is that, for instance, in math, it'd be something that'd be able to read a theorem or to verify a proof, or to do logical computation and so on with using symbols, right? You will have you understand what is a parameter A, parameter B, you understand the notion of A plus B and so on. So you can manipulate symbols. Okay? So given that, the strength that is transparent and interpretable, well, usually can read the code of what the symbolic system might come up with. You can it's more transparent. It often has some logical capabilities, right? And often these are rule-based problem solving, right? So this is usually it's written from scratch. And sometimes it can come up as a computer language. So earlier computer language were like Prolog in Europe and Lisp in the US. And all these things are still around, maybe not widely used. The limitation is that they're a bit brittle in real world scenarios. Like very often, you have to think of all the possibilities in your program. If it's not in your program, you wouldn't be able to solve it. When things are not ambiguous, historically, it was not very good at solving it. Usually be like black and white, is like true or not true, right? I assume they must have thought of some models that can handle like probabilities and so on. It cannot learn from data. Usually, it's like because it's written like math, right? So there's no like empirical data in that. That is a traditional symbolic system, and it requires manual rule creation. So it could be like a program like Prolog. You have to be written by hand. Okay? So you understand that thanks to the internet, right, and the power of compute, this gave a huge leverage to neural networks, right? But not too much to symbolic AI because the bottleneck is really like human manual rule creation and all these rules that you have to create by hand and write by hand, right? So a lot of compute doesn't really help you, a lot of data doesn't really help you, right? So the key goals of Neuro-Symbolic system is to enhance interpretability, improve adaptability. So it's more coming from the symbolic side, like make the system generalizable across domains. Stronger reasoning, right? So the symbolic is very good at reasoning, and AI are becoming like better at reasoning, but still not perfect. And maybe the most important, improve accuracy, right? So when you use an AI today, they don't guarantee you the results, right? So you always have to verify the results and so on. Why? Because they cannot certify the accuracy of the results 100%. Whereas like on symbolic side, sometimes you can't certify the result. It's like 100% correct, especially in math. Okay. So yeah, maybe I'll skip that for neural networks on symbolics. I talk about that. Neural networks. So do you have AI? So this is like a table that gives like that ranks all the LLM models on a rank for different like type of prompts or different type of test, right? So here you see the Anthropic Claude is number one, and this is done by doing like pair comparisons, right? Users compare like give a prompt. They're given the results of the prompt, given the two models, and they say, I prefer A to B, right? And then this allows them to build some Elo system of ranking, and this is how they rank these models. So you see, as of this is like maybe yesterday or 2 days ago, Claude was number one. Then you have Gemini, Grok. Usually they tend to be very close. Gemini, Dolan, I'm sure Claude, Grok. So most of them are like a proprietary system. Then you still have you see some open source model. I guess like GLM might be open source, I believe, it's from China. Ernie is probably from China too. Quen is open source from Alibaba, Kimi, but so they're not in the top 10, but they're not bad for application. They're perfectly fine. The second system, I talk about symbolic system, so let me skip this. But we can see the application for expert system or decision support. theorem proving. So we can talk about this. Planning and scheduling. Right? So you have special programs that handle planning, like PPDDL. I gave a presentation on planning. You can refer to that. The knowledge graphs are used today. Right? So give relationship between entities. For instance, person X invented that product or funded that company or invested in that company, or that person X works for that company. These are like relationship that you can input into a graph, right? So here I'll do a small detour into something called lean. So if you're not a mathematician, you might not have heard of this. That there has been a revolution happening in math, and this comes in part from this system called lean, right? So lean um, is a language that allows mathematicians to formalize mathematics, right? So mathematics today is written. There's math notation that's mostly written in English or in a natural language, right? You read the math articles. It's written in English with some math notation, right? It's written mostly in English. So this is not something that computer will. I mean, computer can always read it, but we read it as a text or a LaTeX file. LaTeX file is more like for scientific notation, but something similar. But it's not something that you can really read as a program, right? So the idea of lean is to translate like a natural language sentence written in math into something that is like formal. Right? So here you see that an example here. So you can see in a math article or textbook, a prime number. A prime is a number larger than one with no trivial divisors. Right? So you can divide only by itself or by one. It's a prime number. So this is written in English, right? But this you cannot give it to Python, and Python cannot do anything with it. So lean translate this into this as a definition, right? Definition of is prime, right? So you as an input you put like n, a natural number, right? And the other kind of test, right? So that any number k smaller than one, bigger than one but smaller than number n, but then the number you consider. So like for all k numbers smaller than n, it cannot divide the number n, right? So this is like a lean sentence, okay? And so lean, the power of lean, it can prove theorem, it can verify theorem. So a theorem, let's say every number larger than one has a prime factor. Right? So this will be a theorem. So you can write the theorem is lean, right? And then, in fact, you can prove it also in lean. So I won't go into the proof and so on. But the idea is that you can prove and you can verify proofs, right? So if I read, like I have a math article, you can translate the proof into lean. There's lean what they call a verify a kernel that will like verify the proof, right? And it can tell you at 100% accuracy that it is correct and not correct. So they call it a verified kernel. Why? Because that kernel is a few thousand lines of code. This is the program that verifies the proof. What has happened in the past? Lean is not the first theorem proof system. Right? There have been systems before, but there are systems before where there were bugs into the kernel, right? So some system would like say, I certify this proof is correct, but in fact there were like bugs in the theorem prover. So in fact it was not true, right? So this is a big problem, right? So at least in lean, the kernel is very small. It's a few lines of code, and people can read it and they can check it, right? So it's not like something that has like 100,000 lines of code and nobody has read it and there's no bug. So this is verified, and many expert mathematicians has verified the code, and this is correct, right? So they're sure that it is correct. So this is lean. And the second thing that has made lean very powerful is that the MathLib is a kind of a library on lean, right? And MathLib has a collection of over 170,000 theorems, right, with proof, right, already in lean. So it means when you want to write a theorem, you can call an already like proven theorem in MathLib, right? So sometimes you do math, or you don't want to reinvent everything, from zero. I can say, okay, there's theorem A that people know. I can use the results. I can prove theorem B, right? So they have that library, and then people are still adding like new libraries, right? So this makes math with AI very very powerful, right? Because it's formalized. Before jumping to how it is done. So there are like different approaches, right, to combine neural approach like an LLM with a symbolic method. There are many more. There are more than that, but I focus on the main ones. So you have symbolic model that feeds into neural networks, right? So it means that a symbolic system can create knowledge, right? Then get encoded into neural networks, right? And then go into training. Right? So this is one system, right? So you can imagine a system. I show like all the theorems to lean, the proof. Then I translate this into. Then I put this into neural networks. So in fact, like system like Gemini and so on, the recent versions, they probably can understand lean, right? And they can. And some, I think, the most recent version can even, like, in fact, translate a natural language math article into lean. I know they can do it perfectly, but at least I think the aim is for them to do that, right? The neural networks can understand symbolic system and kind of integrate this into the all neural networks. Second approach, you have neural networks that can then extract. So then I said that that Gemini can translate natural language into lean. So here we like translate it to a lean, and then it can go into the lean system, right, to do proof and so on. This is one approach to do that. Another approach is to for neural networks to call a symbolic system, right? Let's say there's like a symbolic system that works pretty well. Let's say lean, and then the networks will send command to lean and get the results back. Right? This is also another approach, right? And the hybrid architecture be end-to-end, so everything is integrated, so it's like all into one system. And there's so a bit like we have reasoning module into neural networks today, right? You have like a deep think model has a reasoning, so it's integrated. So you can imagine like a symbolic system integrated with a reasoning module and integrated into the LLM, right? So today, for instance, when you call Claude, you can choose the option deep think, right? Deep research, right? And then it will do the traditional LLM, plus it'll do the reasoning stage all in one go. Right? So yeah, just add on this. So I talk with hybrid architecture is that for training now they also use reinforcement learning, right? So how you train like good reasoning models? If you want to include symbolic system, it will give you some answers, and then you can say the answer is correct or not correct. You can even go through all the intermediate steps. This is the good like way to find the answer and give a 1 or a 0, and then train the model, right? And then the model can learn what are the good approaches and the bad approaches. Okay. Another way to do that is to this I mentioned before to include like knowledge graphs. I don't know if I have time to cover that, but so today you have neural networks that can call knowledge graphs. So it's a way to use some symbolic system. Right? You can even say like knowledge graph is like a symbolic system, right? Because you have different entities and relationship. Challenges on trade-off. I talked about this before, but for the symbolic system is that it can become a bit complex, the traditional one, right? So that's why historically, like, symbolic system is only maybe 10,000 lines of code, and so maybe a bit more, but it's not like it doesn't use it doesn't use data. Some of them need a specialized hardware, and and there's not a lot of data, in fact, for symbolic system. Up to recently, in fact, you'll see that in math, in fact, there's a lot of like data, especially synthetic data. So we have been able, researchers have been able to create synthetic data to be fed into a symbolic system. So this is not true anymore, at least in math. So very often there's a trade-off between interpretability and scalability. So neural networks are very scalable, but sometimes they lack a bit of interpretability because the system are so big, while the symbolic system are smaller, right? They're more difficult to scale, but they're more interpretable. Okay. But you see that maybe there's a happy medium between the two. Right? You see that later. So let's start with math. We talk about lean. So how do we want to use AI for math, right? So the dream or nightmare, I don't know, is to replace a mathematician with AI or to build, I mean, the best outcome would be to have AI collaborators or assistants to mathematicians, right? Professional mathematicians, be able to write papers with the help of AI assistants so they could AI could, for instance, generate proofs for small lemmas, theorems, and so on, or check proofs, right? Mathematician can come with a proof, say, okay, AI, please check that proof for me, so validate the proof, or give ideas, right? You say, okay, how to prove a lemmas, and the AI will tell you, okay, why don't you try this several steps? It has worked in the different domain. Maybe it will work in the in you, so there are different patterns that maybe you don't realize. And it's very common because, I mean, the field of knowledge is so big, even in math, right? Sometimes you might not be aware of other branch of math, or sometimes math done in other countries, and so on. So in fact, historically, it has happened that some mathematicians in the West have rediscovered theorems that have been like already proven in the East and in the former Soviet Union, and so on, because they were during the Cold War. There was a limited communication. There was no internet and so on. Articles were published in Russian and not in English, right? So this has happened a lot in the past. More recently, is more it's more easier to check other people's research, right? Because everything is in the internet, archives, and so on. But the big problem is the volume of research. There's too much research that is not that the human cannot read. I mean, you cannot. It's very difficult for you to keep up in your own field of domain of research within math, right? So AI could be very useful for that. Okay. So we are going to go over like an AlphaProof that combines the neural networks to generate answers with a symbolic system for verification. So the symbolic system based on lean. Okay. So AlphaGo, AlphaZero, so they are important. So here's more as a reminder, the role of reinforcement learning. I could say that this is somehow a neurosymbolic system, right? So it's combining neural networks. And neural networks have been used to build for this Monte Carlo tree search, right? So so neural networks are used both ways. They're used to suggest plays like moves, right? They suggest moves, and they assess probability. What is a good move, right? So the one network is used for that. And a second neural networks, and these two neural networks, in fact, share some layers. Secondary networks will assess the probability of the value of the move, or the probability of winning a game, right? Given the state of the game, of the state of the board. Now, what's the likelihood that player one is going to win against player B, right? So they are the value, a policy network and a value framework. This is how it is it is used in neural networks. But at the same time, there are like specific rules, right? The rules of the games and so on. There's like there's symbols. You could say it's also a symbolic system, right? Like there's a specific way to play. You cannot play any way you want, right? You have to respect the rules, the boundaries, and so on, right? So, and these ideas of using reinforcement learning, right, to train networks have been used a lot. You'll see in these subsequent models. Okay, we talk about lean. So here also, just to, if you're not mathematician, you haven't done math, I mean, maybe you have heard of this. So you have what they call the IMO, right? So International Math Olympiad. So these are like international competitions, a competition at international level. So more than 100 countries participate. So the US participates every year. So maybe last year, I think 110 countries participated. You have like US, China, South Korea, France, all the major countries participate. And so you send six students, right, to that competition. Six students with a coach, assistant coach, and so on. There's a team that goes with them. And these are like high school students. So pre-university. These are not like college students, pre-university students. And usually they qualify, so they have their competition in the US, a competition at city level, regional level, state level, and so on. And the best, they are selected to be part of this that team of six. So for the competition, so there are like six problems, right? So I've listed the six given. I think it was given last year. So you can try to give to answer them. By the end of the talk, you tell me if you find the answers. You're not allowed to Google them. Right? Okay, the answers are online, but you can find them by yourself. You tell me. So there are 7 points per problem, 6 problems, so maximum score of 42. And if a student gets a score bigger than 35, right, so it means like he solved 5 problems or more, he get a gold medal. Silver medal if you score more than 28. Bronze medal if 19, and so on. They have like so okay, so if you get like you want to hire someone, you get a gold medal, or like any medals, in fact any medals at the Math Olympiad is quite impressive. And if you read this, so even though technically it's not because it's only high school math, right? But still these things are not trivial to solve. And for some of them, I think some math coaches that it took them hours to solve by themselves. So usually the math coaches, they're good, they're former like medalists. So they can solve this kind of thing, but sometimes it takes them hours and hours to solve it, right? So it's not trivial. So for many years, it has been a benchmark for AI in math, right? To solve this. At the same time, you see the weakness that this is only like high school level mathematics. So it means that the tool that they use are kind of old style tool. I mean, it's tool that stuff that you teach in high school, so, which is not really like top research like math, right? What you learn in high school. It's more math from maybe 2 centuries ago or something like that, right? So it's like maybe 2 or 3 centuries ago. So a lot of math, the calculus. I don't even know there's probably not a calculus in there, but a lot of math that we teach in high school have been invented in the 18th and 19th century, right? So it's kind of old style math. Huh? Okay, let's go into AlphaProof. So it is designed to solve complex mathematical problems by generating formally verifiable proofs. So they use a lean for that. So use Gemini, right, as a LLM, and Ling as a proof assistant, right? So Gemini generate like many proof steps, right? Many possible solutions, right? And then the lean checks every proof, and then select the proof that is correct, right? And tells you the proof is correct or not, right? And then and uh, and then for the proofs, so the proofs to write the proof, they use what they talk about tactics or moves, what to try, right? Try it. So HyperProof has two components, a bit like AlphaGo, right? It's not surprising. I think some of the scientists who work on AlphaGo work also on AlphaProof. Right? So you have the same kind of idea. So you have policy networks. Policy networks is to give the strategies they say. Okay, so it's not it doesn't tell you the move that you have to do in Go, but what tactics, what kind of new parameters to use, and so on. So we will do that. And the value networks will use what is the likelihood that you are going to find the solution of that that theorem, right? And then it is trained by reinforcement learning, right? So we know that it's something is correct or not correct at the end. It's how to train. So the policy networks and value networks are trained like that, right? So here it tells you like how the problems were created. So a lot of it came from published problems and solutions, right? Then many of them have been like written into MathLib on Lean. So you have like a written proof into Lean. So this is very good to train the models, right? And uh, then they created like many synthetic problems, right? So created by Gemini. And then they, with the help of Gemini, created a lot of proofs, then verified some of the proofs. So not all the proofs are not correct. Verified that some of the proofs are correct. Then you have pairs of synthetic problems with synthetic proofs, which are deemed like correct. Then they re-inject it in the training model, right? So then suddenly you have like a lot of like synthetic problems with proof, so that it can generate a lot of data. So that's why you are able to train AlphaProof. Okay. So that is why you try to real problems, generate synthetic problems and proofs that you re-inject into the training set, then you can train the reinforcement model. So here, this is so here, this is like an example of that they use in AlphaProof. So here, so they define what they call a Aquasulian function. So a function means that f of x plus f of y is equal to f of x plus y, right? Or f, so f is a function, right? F of x plus y is equal to x plus f of y. So if a function f verifies this, it's an Aquasulian function, right? So the theorem, the goal, smallest parameter c, so that f of r plus f of minus r is finite if r is under the parameter c, something like that. Right? So this is a problem. So you have to find that c, and AlphaProof is able to do that. I guess that 99% of people cannot solve that. I mean, if you're not professional mathematician, it's probably difficult to do that. Okay, the second thing is so AlphaProof, a weakness of AlphaProof, it cannot do geometry. Right? It doesn't do geometry. In Math Olympiad, you have also geometry problems, right? So AlphaProof by itself cannot do IMO problems. It couldn't complete IMO because it couldn't solve geometry problems. So here come AlphaGeometry. As it happened, so they all come from Google, DeepMind. So as it happened, a team was working on solving on using AI for geometry. Just coincidence. So it's a theorem prover for Euclidean geometry, Euclidean plane geometries in 2D. It doesn't do 3D. So it's also used the same idea. I use neural network, neural language models to suggest. So in geometry they don't talk about moves or the parameters, what they call auxiliary construction, right? So let's say you have a triangle A, B, and C. Then you insert a new parameter E. There will be, for instance, in the middle for A and C, for instance, right? or you draw a new line, right? You do a new circle. So it's a new like a construction, they call auxiliary construction. And very often to solve geometrical problems, you need this auxiliary construction, right? So here, for example, at the bottom, so I don't know what they have to solve. But you start with a simple triangle, and then you build the circle, then you use the projection of C over like the line A and B, right? Or you do the parameter C could be like a center of a circle and so on. So you have like a lot of like new like parameters that you solve, intermediary steps that you use to solve to solve your theorem. Okay. So here, instead of using lean, they use something called DDRR, it's called Deductive Database Arithmetic Reasoning. So something that's done internally, but it is that they have reused properties of a language called like data log. That is also inheritance from Prolog, right? I mentioned Prolog on this before. So you have data log. So they use something from that to formalize like data and put things into the database, right? So I won't go into detail, but so the idea is that instead of using lean, they formalize so relationship like say AB perpendicular to CD, right? So it's written in that language, DDR language, perpendicular PRP, ABCD. This means AB perpendicular to CD. AB parallel to CD is a PRRL, parallel, right? ABCD, etc. Collinear, etc. So they formalize all these things. This language, then they can do like programmatically try to solve this. Okay. So the detective, like so, starting with the base of this hypothesis, that language can say, okay, it can deduct all the consequences, all the things that it can derive from this hypothesis. Right? So that's how they did that. So for AlphaGeometry, so at least for the Olympiad for the geometrical, it can solve only geometrical problems, right? So it could solve like 25 out of like 30 international math problems, which is a bit lower than gold medal, but very close to a gold medalist, right, on geometry. So yeah, so this is the idea, right? So you start with the geometrical problems. Then you have to solve so I'm not sure where to solve. So maybe you have to solve. Okay, maybe you have to solve that H. Okay, that HA. Okay, so here you have to solve that HA is perpendicular orthogonal to BC, right? And so you start with this. So prove that HA is perpendicular to BC and the H is considered like this. So in fact, all these things are written into the DDRR language, and you have a symbolic deduction and trace back, right? So it tries to deduce all the consequences from this hypothesis. If it doesn't lead to anything, it traces back, right, and reiterates, right? This is how it's solved the solution. Okay, I won't go into AG2. AG2 is an improvement on AG1, so it's the second version of AlphaGeometry. So they one challenge that they had with AlphaGeometry is to formalize this problem set. So some of these problem sets were not easy to formalize. So since they couldn't do like locus problems, things that is moving. So point A is moving at that speed, point D, and why they to interact, all these kind of things, or this, they couldn't solve these kind of things. So AG2 improve on that. They had a stronger DDR system called DDR2. Faster algorithms, it was written in C++. The other one was written in C, I believe. More training data, right, and more complex proofs. A better search algorithm. So before it was like for that. So before, so they have different solutions. So they will AG1 to the first AlphaGeometry just use like the top 10 solutions and try to select the best 10, right? So on a single tree, what they call beam search. AG2 use some parallel trees. They will do things in parallel on these. So different trees exploring different solutions. It's like different mathematicians working on the problem at the same times, but these mathematicians would share their results, right? Intermediate steps, and they would still these trees will share the results. So IG2 will be much more powerful. Okay, so this is like the idea of like different trees working in parallels with a shared workspace, right? So this is kind of a thing that they can prove, and you can see, right, all these like red and blue are probably intermediate steps that you have to introduce to prove the results, right? Okay, so I want to talk about Aletheia, also from Google. So Google doesn't do everything, right? But hey, I found that in that field, Google did some very interesting research. So Aletheia is now the current version probably use Gemini DeepThink as a LLM. It's a three-agent system. So that operates in a natural language. So there's no pure symbolic system. So it has a generator, right? That proposes a solution, right? So usually, deep be say Gemini deep thing or Gemini will propose solution. A verifier, they will checks for flaws, right? A reviser, correct errors and tries again. Okay, so this is what you see here, right? So they really get inspiration from AlphaProof, AlphaProof on AlphaGeometry, that you have an LLM that can generate with solutions, ideas, and then a verifier, even though here it is in natural language, right? And the reviser, right? So it's like it's an agentic system with three agents, right? You generate candidate solution, you verify, you see that there's some critical flaws. Okay, send it back. Or sometimes you could like easy just like minor fixes. We give a revised solution and then and mix it and then verify again. Okay. So this is from a paper on to do autonomous mathematical research. Okay. So given that so this autonomous, there's no human involved, right? So they are given that they're able to create some publishable research. So they are not so as of today. So they use also ranking of level of interest of this or novelty. So they do level 0 to level 4. So they get inspiration from autonomous driving. Autonomous driving has the same thing, or level 0 to level 4. Level 4 would be like purely autonomous driving. You don't know, you can sleep in the car. So here they use it in terms of novelty. Zero like negligible novelty, and level 1 minor novelty. Level 2 is like it's not that novel, but it's publishable. Like some venue will publish your paper, right? So they found so as of today, Aletheia is at that level of research, right? Publishable research. I guess undergraduate students who's very good at math could probably produce this kind of research, right? But maybe for PhD or professor, you expect something better. Okay. So something that has happened just this month is first proof. So first proof. So it is an experiment designed by some human math professor from Stanford and from top math department. So what I noticed in the past that many like AI system in math, they were saying, okay, we have this new system, that is very good at math, and to prove it, we beat all these benchmarks. A lot of many benchmarks you saw in the LM Arena table. You have a column for math. That's what they said for. So you have a math benchmark. So you are number one. So for these math professors and other people too, sometimes it can be a bit skeptical. Could you have leaks? Right? Some of the results might be known by the AI, especially the older benchmarks. If your benchmark has been around for a while, it's very likely that at least some, not all of it, but some of the results have been leaked, right? Then the neural networks just reproduce the solutions. So to make sure it doesn't happen, so what they have done, say is that altogether they have worked on 10 research level math questions, right? In math, right? And that come up from their own ongoing research that have been solved only by the author, right? With a proof. This is like lemmas level of problems, right? That never been posted on the internet, right? So there's no leaks and no data combination. So so these guys are experts. So they say on their own research, they know that this thing has not been done before, right? And they have the proof, and so they have published the problems. They have encrypted the solution, and they have released the solution on February 13. Right? So they say, okay, these are the problems. We give you the solution February 13, and all the assistants are there try to solve it, or even humans can solve it too. Right? So humans could also try to solve it. So committee was invited to test, but it's really the objective to test the assistants. Are they really as good as they say they are, right? So this is one sample problem. It's like the first problem of the first two problems of these things. Okay, so I'll spare you reading this, but these are not a trivial questions. Right? It's like things that top like mathematicians from Stanford, etc., Harvard, and so on came up with. Okay. So we talk about Aletheia. So Aletheia tried to solve it. So the Google team tried to solve it with Aletheia, and what they said that they have solved 6 problems out of 10. So they couldn't solve 10 out of 10, but it's not bad, you know. I mean, it had been 0, it would have been embarrassing, right? But they said they have solved 6 problems, right? So using a 2 version of Aletheia, one using the deep Gemini 3 deep think, and one using the base model of Gemini, right? And they take the best of the 2 answers, right? So fully autonomous. So no human intervention. The only intervention was at the end. They have an expert evaluation to so you have 2 agents, 6 candidate solutions, and you just take the best of the 2, right? Of the 2, and then as a final answer, right? And then it was reviewed by independent experts, and then for the majority of experts, he has solved like 6 problems. For one problem, so for many, like they were all like there's a consensus that Aletheia has solved the problems. Maybe for 1 or 2, maybe there's no consensus, but the majority still say that Aletheia solved the problems. So this is quite impressive, and I can imagine that next year or the next round, they work on more problems. They can introduce more things. This system can be improved, and maybe one day we do a 10 out of 10. Right? Okay, so I'm going close to the end. So the Gemini Deep Think has been used in collaboration with scientists to see how scientists can use deep like a LLM, deep research for real science, right? For real scientific research. So here I took, so there are like different case studies and so on. So I took one in yes, this is physics, right? In physics, and see how they use it. And you see it is kind of same idea as a Neuro-Symbolic, right? So okay, the problem is computing the gravitational radiation emitted by cosmic strings. Okay, by cosmic strings. Okay. I did physics undergrad, but I don't remember. This is kind of I'm not sure exactly what it is, but okay. So you have to calculate the integral. Right? So say you have to evaluate the notorious difficult integral over a sphere. Right? So this is like the thing that you have to calculate. Integral is plagued by 2 obstacles: severe singularities at the pole and wildly oscillatory behavior at high frequency that defeats standard numerical methods. Right? So in fact, this physics is really a math problem. Right? So how do you calculate this? Right? So they use so in fact, the researchers came up, so they use the LLM, right? And they paired with a tree search algorithm. So very similar to what we've seen before with the AlphaProof, AlphaGo, etc. The three search. So the idea is like the Gemini deep thing will generate like many answers, and then so suddenly you have a mathematical expression, right? It will code it in Python, and it will test it, and then it will fail. It will fail. There will be some test to see if it succeed, if it is stable or not. And if not, it get pruned, and then it will come up with other solutions, right? So it's a bit a brute force approach. Then at the end, one will come up with they manage to come up with a solution. But it's not bad because then you can do the computer can just work on your prime set while you're like sleeping at night, right? And you come back in the morning, say, okay, I tried 1,000 solutions, and 5 seems to be correct, and you can just manually check, and then it makes a big difference, right? I'm going to skip knowledge graphs. We don't have much time, but just the idea is that today an LLM can not only can use a knowledge graph, right? So data can be stored into knowledge graph, but it can also encode knowledge into knowledge graph, right? So in fact, some knowledge graph use LLMs to encode data. The problem with knowledge graph, it can become obsolete, right? You need to know like what's I say is what's his name? Andrew Windsor is still the Prince of England, right? So then you have to know that recently he has been demoted. So you need a knowledge graph that can read the news, and then say, okay, no, the Prince Mountbatten is not he's not the prince anymore, right? So you need to be updated. So now you can use LLM to feed to the knowledge graph. So the last one of the last couple of slides is that you can say that, in fact, knowledge systems are already there and they're already used, right? So why would I say that? So, in fact, one interpretation of Gemini deep think, remember this the fact that, or at least the Aletheia system, right? On the so the Aletheia on the deep thing using Aletheia, if it's using Aletheia. So today, I mean, it's very active field of research, right? So first, the results I gave you about Aletheia, it was published 2 days ago, right? On this, they must be very like they're working intensively on this, right? So from how to so Aletheia could say consider a neuro-symbolic system. How do you how does Gemini deep think integrate this notion of the verifier, right? Verifier into the system, right? So the verifier act as the neuro-symbolic neuro-symbolic logical check, right? So I give an answer. So I give an idea to Gemini deep think. It go over my idea, verify it, right? Not in math, but we verify that it makes sense logically, right? Say, okay, these are some flaws into my reasoning, and give me back, okay, my reasoning is not correct, or some empirical data contradicts what I need to do, suggest improvements, and then I can come up with a new answer, and then it can come up with answers by its own, right? So you see that now the Gemini did think, and now these new reasoning models, I believe that all the reasoning models are going to use something similar now. Just to remind you the system, right? Right. You generate, right? You have verifier and reviser, right? So I believe that all the systems are going to work this way. A reasoning system that does verify answers can revise, and regenerate answers, right? So the symbolic system, in fact, is a neural networks, but it's trained to check answers, verify, and revise and update. Okay, so you could say that, in fact, neuro-symbolic system is not a pure like theoretical idea. It's already it's already there into the most powerful like AI system, like Gemini did. It is already in there, not exactly like it was in the AlphaProof or in the original system, but the idea is already into Gemini. I'm sure the Gemini 4 will have this embedded into the system. So when you do that, you understand why Google is quite confident they can reach AGI and ASI in a few years. It's artificial super intelligence, because I think that this is going to work. I mean, this looks quite convincing to me that this is going to work. As having the AI verify answers, double check, revise, and resubmit answers. So have all these ideas of using reinforcement learning, tree search, on how to build a symbolic system based on natural language. This could work very well. Okay. Uh, so so just key takeaways, right? So symbolic system combines pattern recognition of LLMs, the logical reasoning of symbolic systems. So the extreme is to build neural networks to do the logical reasoning, is what Gemini, Google is doing. So you have the strength of both systems, right? I didn't mention it, but you can see it in the slides. It's really also the idea of merging system one and system two, right, of thinking, right? That you use in psychology. System one is the intuitive answers, right? So the neural networks today, system one gives the answers right away. System two is the reasoning, verification, updating, double checking, and so on. This is the system two. The symbolic system is doing the system two, but the verifying system, Aletheia, of Google, is doing that role of the slow thinking. Okay. So you could say the geometry deep thing, at least the Aletheia component, could be considered like a pseudo, like a neurosymbolic system. So it's already there, right? So there's still challenges. This is still a research stage, even though geometry deep thing can be used today, right? Maybe in paid subscription, we can experiment with it. But in the future iteration, Gemini 4, I'm sure it's probably going to be in there, right? So it's really like, so we have moved beyond the simple LM predicting the next world. We have moved beyond that. So we are really in the area of AGI and soon ASI, right? Into where the system is there. So that's why you remember the cartoon that I showed you at the first few slides. So you saw this neurosymbolic system. It could be a crossover of like the mouse and the cat, right? So Jamie the cat and the bodybuilder as a mouse. So this is like maybe the few. Maybe this is AGI, right? No, the future AGI or ASI. Okay. So I'm going to stop here. I think you're running out of the time. So just to advertise a little bit. So my second book has come out, right? You can scan this QR code if you want to have a copy. So here I talk about, so the first one was more pure LLM, the basic of LLM. Second, part two was talking about AI, reasoning models. So a lot of it is based on the talks I gave last year. Reasoning models, planning, using tools, multi-agent system, and so on. And part three is going to be published. So I say it's going to be published when AGI is going to come out. And it's going to be published probably sometimes next year, 2027. I will incorporate some of the stuff I present today. So some of it, sometimes I write chapters as I prepare this presentation. At least I think about the chapters I'm writing when I present this presentation, right? So Neuro-Symbolic system is very exciting. So it's not pure theory; it's already there, in fact, right? In the frontier models, so something that we should follow very closely. Next month, I'm not sure about the topic. It's very likely I'll be talking about word model, and I think a lot of research done, interesting stuff has been done here. Okay. So I stop here. I don't know if you have any questions. If you have any questions, raise your hands. Otherwise, we'll stop here. I encourage you to read the papers, the Aletheia papers, and all this research from DeepMind. I focus on DeepMind because I find it just the most exciting, but a lot of people have working on something similar. Right? Okay. I'm going to stop sharing. So thank you very much, and talk to you next month. Okay. Goodbye.